This is Dr. Ritu Singh from Basic Science Department, and today we are going to discuss nanomaterials and part 2 of nanomaterials. Now in the previous lecture, that is part 1, we have discussed what are nanomaterials, what is the importance of nanomaterials, then how many types of nanomaterials are there and what is the synthesis. So nanomaterials are the materials where the structural component, one of the dimension, at least one dimension of the structure component lies in nano range. Nano means 10 to the power 9. So the study of nanomaterial is nanoscience, and when we apply or when we study the application of nanoscience, then we have nanotechnology. Then we have got different types of nanomaterials, quantum well, quantum wire and quantum dot. If one dimension lies in nano range and the two dimensions are normal, that is quantum well. And when two dimensions they lie in nano range and one dimension is normal, that is quantum wire. And the third one is when all the three dimensions they lie in nano range, then we have quantum dots. Then the synthesis of quantum dots can be done by two ways: top to bottom or bottom to top approach. So from bottom to top we start with an atom and then we keep on adding and we get a bigger structure, for example a human body. From top to bottom means just like making a sculpture, we start with large material, but when we end up after making this sculpture, the material which is used is less. After that we had preparation of nanomaterials. In preparation of nanomaterials we had ball mill method, then laser beam method, radio frequency plasma method, sol and gel method was there. So the fifth one was sputtering. So these were how methods how we can prepare nanomaterials. In the second part of nanomaterial, we are going to discuss the examples of nanomaterial, carbon based examples of nanomaterial, and after that we are going to discuss applications of nanomaterials. Now I start with examples of nanomaterial, and before the first example which I am going to take is fullerene. So a fullerene, it is a polymorphic allotrope of carbon. We have got two allotropes of carbon, normal allotropes of carbon, which are diamond and graphite, and fullerene is polymorphic or polymeric allotrope of carbon. It is one of the Archimedean solids. So Archimedean solids, we have got 13 Archimedean solids. By Archimedean solid we means Archimedean solid is going to be or is formed of more than one polygon. For example, if we take graphite, graphite is either made having a hexagonal arrangement of carbon, or it can have rhombohedral, which is synthetic graphite. But Archimedean solid means we are going to have two types of polygons. So the type of polygon may differ. So we have got 13 Archimedean solids, and fullerene is also one of them. So fullerene is an Archimedean solid. Secondly, the discrete molecule of fullerene is actually a cluster of carbon atoms. So we have different types of fullerenes like C20, C24, C32, C36, then we have C40, C50, C60 and C70. So these are some of the examples of fullerenes, in which this is the most useful one, and it is known as Buckminster. So these are some of the examples of fullerene, out of which C60 is most useful, and it is also known as Buckminster. So actually fullerene is a polymeric allotrope of carbon, where the discrete molecule is not having single carbon, but it is having cluster of carbon. So a single molecule is having cluster of carbons, and these are the examples. C20 is the smallest one, and C60 is the most useful one. Now when we come, next we come to the structure of fullerene. When we talk about the structure of fullerene, it is having a structure of football. We are having pentagon and then we have hexagons. So as I said, it is an Archimedean solid, and Archimedean solids have got two polygons. So the polygons which are present are pentagon and hexagon. This is how we are going to make the structure. So actually the structure of fullerene is truncated icosahexagon. Under this, it has got 32 faces plus it is having 60 vertex. So 32 faces. In faces we are having two polygons, one is hexagon, the other is pentagon. So this is a pentagon and here we have hexagon. So 32 faces, 20 are hexagon and 12 are pentagons. 20 hexagons and 12 pentagons are there. Now as we can see in the structure, we cannot draw two pentagons adjacent to each other, but we can draw two hexagons adjacent to each other. So I have drawn a pentagon and around that I am drawing hexagon, but I cannot draw just reverse of it. I cannot draw a hexagon here and then pentagons around. So a condition is there that we cannot draw two pentagons adjacent to each other. So this is the structure of fullerene. So structure of fullerene is known as truncated icosahexagon. It is also known as or referred as geodesic dome structure. And the specification is it is having 32 faces and it is having 60 vertex. Out of 32 faces, 20 are hexagons and 12 are pentagons. And when we draw this structure, two pentagons cannot be drawn adjacent to each other. And with this structure, it is also known as buckyball. Next we come to the preparation of fullerenes. Now regarding preparation of fullerene, the whole preparation is done in an inert atmosphere. Why the inert atmosphere is taken is actually fullerene is a cluster of carbon, but basic structure is it is having carbon. So if the atmosphere which is taken is oxidizing, then carbon can be converted into either carbon monoxide or it will be converted into carbon dioxide. So we do not want it. So therefore we take inert atmosphere. So the atmosphere, we either take helium or we are going to carry out the whole preparation in the presence of argon. So the first condition is that the preparation is carried out in the inert atmosphere of either helium or carbon. We are not going to use oxygen or normal condition or normal preparation in the presence of oxygen is not done, because in the presence of oxygen, carbon is going to react with oxygen forming carbon monoxide or carbon dioxide. So what we take here is we take two graphite rods. After taking the two graphite rods in an inert atmosphere, an electric spark is produced. As the electric spark is produced, the graphite rods, they evaporate in the form of dust. After the dust is formed, it is mixed with a solvent, and after mixing it with solvent, we can we get, after the mixing with solvent, we get mixture of fullerenes. And these mixture of fullerenes, they can be separated either by sublimation or by chromatography. So it is separated by sublimation or it is separated by chromatography. So this is the whole process of formation of fullerenes. So we take two graphite rods and we produce an electric spark in an inert atmosphere. Why we are using inert atmosphere? Because otherwise it is going to react with oxygen, forming either carbon monoxide or carbon dioxide, because the basic component which is present in nanomaterials is in fullerenes actually is carbon. So we are using inert atmosphere. For the inert atmosphere, we normally use helium, or we are going to use argon for that matter. Then we produce an electric spark. When the electric spark is produced, the graphite from the carbon rod is converted into dust and it evaporates. Then this dust is mixed up with solvent, and after mixing up with solvent, we get mixture of fullerenes, and this mixture of fullerene can be separated by either sublimation or by chromatography. So this is preparation of fullerene. Next we have properties of fullerene. Now regarding properties of fullerene, the first property is color. The color can be of mustard color. So smaller fullerenes, the color is mustard or it is brown color. But as the size of fullerene increases, the mustard or brown color changes to black. So this is the physical appearance of fullerene. So in physical appearance, color, the small fullerenes, they are of mustard color, but as the size increases, the mustard color changes to black. Second property is they function in pure state, they function as an insulator. But to fullerenes, if we add alkali metal, then they are converted into superconductors. So we can write the second property is they function as superconductors. Why they function as a superconductor? They function as a superconductor because we are adding alkali metal into it. So when we add to the fullerenes are actually insulators, but when we add alkali metal to them, then they start acting as superconductors. So the second property is they are superconductors when we add alkali metal to them. Third is they can be compressed to lose 30% of their volume without disturbing the cage-like structure. So 30% of volume can be reduced, but after reduction of this volume, the basic structure, the basic cage-like structure of fullerene will not be disturbed. Then the fourth property is to a pure fullerene, if I add an electron donor impurity, so if an impurity is added, which is electron donor impurity, then what happens? The fullerene, it starts behaving as a ferromagnetic substance. What is a ferromagnetic substance? ferromagnetic substance means when we apply to a substance, when we apply an electric magnetic field to a substance, it becomes magnetized, it is going to show alignment. But when I remove that magnetic field, it is still aligned. That is a ferromagnetic substance. We have another substance which is paramagnetic. Paramagnetic means, suppose this is a paramagnetic substance, if I apply the magnetic field, it will show alignment, but when we remove it, the magnetic character is destroyed. So, but in ferromagnetic substance, even if magnetic field is removed, it is going to behave as a magnetic substance. So, it is ferromagnetic substance. So, when I am going to add an electron donor impurity to fullerenes, it is going to behave as a ferromagnetic substance. So, these are the important properties of fullerene. First is the color. The color of the fullerene is, the small fullerenes, they are of mustard color, but as the size increase, the color changes to black. The second is, in pure fullerenes, they are insulators, but when I add an alkali metal into it, or I can say I add an inorganic component into fullerenes, then it will start behaving as a superconductor. The third is, I can compress this, or if I compress it, the 30% of the volume can be reduced without disturbing the cage-like structure of fullerene. And the last is, to the fullerene, if I add an electron donor impurity or an electron donor group, then it can function as a ferromagnetic substance. So these are the properties of fullerene. So if I talk about fullerenes, then fullerenes, they are Archimedean solids. Archimedean solid, by Archimedean solid I mean that it is made up of more than one polygon. So in fullerenes, the polygons which are present are hexagons and pentagons. After that, we have fullerene is a polymeric allotrope of carbon, or it is a polymorph of carbon. Normal allotropes of carbon are diamond and graphite. Polymeric allotrope of carbon is fullerene. It is the discrete molecule, the one molecule of fullerene is made up of cluster of carbons. Then we have got different type of fullerene. C20 is the smallest and C60 is the most useful fullerene, which is known as Buckminster. Then we come to preparation. Then we come to structure. If we talk about structure, it is truncated icosahedron or geodisc dome structure, where we have got 32 faces, 20 are hexagons and 12 are pentagons, and apart from 32 faces, it is having 60 vertex. If we draw the structure of fullerene, then we have pentagons and we are going to have hexagons. Pentagons cannot be drawn adjacent to one another, whereas we can draw hexagons adjacent to each other. Then the next is preparation of fullerenes. If we talk about preparation of fullerenes, then we take two graphite rods and an electric spark is produced in an inert atmosphere of helium or argon. When an electric spark is produced, the graphite evaporates in the form of dust. Then this dust is mixed up in a solvent and we get mixture of fullerenes. This mixture of fullerene can be separated either by sublimation or by chromatography. And next we have properties. Regarding properties of fullerene, we have got it is of brown. Small fullerenes are of brown color, but as the size increases, the color changes from brown to black. Then it can function as a superconductor. If we add an alkali metal into the pure fullerene, it can function as, or it functions as a ferromagnetic substance if I add an electron donor substance or electron donor impurity into fullerene. And the last property is, the size of the fullerene can be reduced, 30% of the volume can be reduced, and the cage-like structure will not be disturbed. So these are the properties of fullerene. So next we have, in the last we have applications of fullerenes. The first application of fullerene is it can be used as a superconductor. So normally it is not a superconductor, but it can be used as a superconductor when I am going to add an alkali metal into it. The next application, it can be used as a ferromagnetic substance. So again, it is not a ferromagnetic substance, but if I add an electron donor impurity into fullerene, it can function as a ferromagnetic substance. Third, it is used in catalysis. Catalysis, for example, in homogeneous and heterogeneous hydrogenation of reactions. So in these reactions, it can be used as a catalyst. And fourth, it can be used in polymerization. Polymerization, for example, if we take C60 and we subject this C60 to 700 kelvins of temperature, the temperature can vary from 600 to 700 plus 1.2 GB of pressure. So this is pressure and this is temperature. And this pressure and temperature is subjected to this C60 for 5 hours. If we subject it 5 hours to this temperature and pressure, then cycloaddition reaction can take place, which will lead to polymerization. So these are some of the applications of fullerenes. Now we come to the second example of fullerenes, second examples of nanomaterials, that is carbon nanotubes. Now if I take a buckyball or a Buckminster or C60 or any fullerene of a very big size, or I keep on growing the size of fullerene, then or Buckminster, then it is converted into a cylinder, and that cylinder, initially carbon nanotubes were known as cylinders, but now after some times in 1991 by Smiley, they were known as carbon nanotubes. So actually carbon nanotube is a buckyball of very large size. So if I have to draw a structure of carbon nanotubes, then the polygons are same as that present in fullerene. There we have got hexagons and we have got pentagons. So if I draw the carbon nanotube, this will be the structure. These are all hexagons, and hexagons are going to form central part of this carbon nanotube. So these are central part of carbon nanotube, and at the corners we have pentagons. This is how we are going to draw a carbon nanotube. I am only drawing one layer just to represent how it is going to look. So this is carbon nanotube. At the center we are having hexagons, and at the corners we are going to have pentagons. Now the difference between fullerene and carbon nanotube: in case of fullerene, we cannot draw two pentagons adjacent to each other, but in case of carbon nanotubes, we have drawn pentagons at the side. If this is a carbon nanotube, then these portions where it is going to close, or upper portion or below portion. So at the center we are going to have hexagons, but when the tube is going to close from the upper part, lower part, or from the sides, we are going to have pentagons. But in case of fullerene, what was there? Two pentagons. We cannot draw two pentagons adjacent to one another. So at the central part we are having pentagons, and at the ends or corners we have got, this is hexagon and at the corners we have pentagons. So, and carbon nanotubes can be closed or it can be opened, or it can be closed from one part and opened from the other part. So, here this is opened from top and bottom. So, this is the structure of carbon nanotubes. Now, based on carbon nanotubes is basically a sheet of graphite. So, and the arrangement in graphite is also hexagonal. So, in carbon nanotubes, what are carbon nanotubes? Carbon nanotubes are fullerenes of a very big size. So, fullerene of a very big size appear in the form of a cylinder. Later on, initially it was known as carbon cylinders, but later on they came to be known as carbon nanotubes, and this is the arrangement or structure of carbon nanotubes, where at the center we are having hexagons, and where the tube is going to close, or upper part or lower part, there the arrangement is pentagonal, or the polygon which is present is pentagon, and at the center the polygon which is present is an hexagon. Now, we have got two types of carbon nanotubes. One is single walled carbon nanotubes. So, nanotubes are basically the sheet of graphite. So, single walled carbon nanotube is first, the second is multi-walled carbon nanotubes. The difference between the two is, if I am rolling the graphite sheet, then if I roll one graphite sheet or one layer of graphite, then we form a single walled carbon nanotube, and if I roll more than one layer of graphites, then I get a multi-walled carbon nanotubes. So, by rolling single layer of graphite, I am getting single walled, and if I roll more than one layer of graphite, then I am getting multi-walled carbon nanotubes. Then this is on the basis of number of graphite sheets which are rolled. We have got two types. So, on the basis of number of graphite sheets which are rolled, or layers which are rolled, we have got two types of carbon nanotubes, single walled and multiple walled. Now, the second classification is on the direction by which we are rolling the graphite sheet. Either we are rolling vertically, or we are rolling the graphite sheet horizontally, or we are rolling it diagonally. So, based on this, we have got zigzag type of carbon nanotubes, then we have got armchair, and the last is chiral carbon nanotube. So, this is we roll it vertically, this is we roll horizontally, and chiral carbon nanotube we are going to roll it diagonally. So, this is the classification of carbon nanotubes. So, we have got two types of classification of carbon nanotube. One is on the basis of number of graphite sheets or layers which are rolled. If it is single, then we get a single wall carbon nanotube, and if we are rolling more than one, then it is multi-walled. Then on the basis of direction of rolling of the graphite sheet, we have got three types of carbon nanotubes. One is zigzag, then we have armchair, and then we have got chiral. The division is on the basis of whether we are rolling it vertically, that is right to left or left to right, or we are rolling it horizontally, top to bottom or bottom to top. And the third is chiral. Chiral means we are going to roll the graphite sheets in a diagonal manner. So, this is all in carbon nanotubes, and next we are having applications. So, regarding applications of carbon nanotubes. Now, if I consider the applications, it is used in device technology. That means it is used in electronic industries. as a microprocessor, and it is used as biochips or bio-NIMs. It is nano electron mechanical system. So this is the application of nano materials in device technology. Second, it is used in health and medicines. Health and medicines means it is used in tissue cultures, which is again a technology. So we are having the use of nanomaterials in tissue cultures. They are used in drug deliveries. Drug deliveries means right amount to the right part of the body. Then it is used in detection of tumors, in the detection of pathogens if they are present inside the body. So these are all the health and medical applications of nanomaterials. The next, it is used in transportations. So in transportation means whenever you are using nanomaterials or nanotechnology in transportations, then it is going to reduce the pollution which is taking place. And secondly, a component or compound which is cerium oxide. If we take a this in nano range, then it can be used as a diesel fuel. So again, this is an application of nano materials. The next application, it is used in energy and environment. Now in energy and environment means they are used to store hydrogen. The hydrogen storage is a problem when we are using fuel cell, because in fuel cells the fuel is hydrogen and the oxidant is oxygen. So the major problem when we use fuel cell is that the storage of hydrogen is a big problem. So if we use nanotechnology in energy and environment, then the storage of hydrogen can be used up. It is used up in the storage of hydrogen. Then we use nano filters. So when we use nano filters, the small particles which are normally left out in filtration, they can also be taken care. So it is used in nano filtration. Next, it is used in energy consumption. So energy consumption means it is going to reduce the energy consumption. So if we use nanomaterials in energy and environmental, these are the advantages. It is used for storage of hydrogen. It is used as a nano filters. We can use it in nano filters, then it is going to reduce the energy consumption. The next application, it is used in space explorations. Space exploration means the space materials, if they are made up of nanomaterials, it will be lighter and they will be more reliable. So it is a good technology to be used in space. The next is, it is used in therapeutics. The use in therapeutics means normally we take up, if we take up drugs or we take up medicines, then they have got certain side effects also. But if we use nanoparticles or nanotechnology, then we can deliver the right amount of medicine to the right part. So that is the use of the next application is in optics. So in optics now we are using it as LEDs. So this is the application of nanomaterials. The next application of nanomaterials is, it is used in sensors. Now if we use nanomaterials in sensors, then they are more sensitive and they are more reliable. Then computers. If nanotechnology is applied to computers, then small computers can be formed, plus again more reliable and more powerful computers can be formed by using nanotechnology. Then the next application of nanotechnology or nanomaterials is dendrimers. It is used as an engineering material, it is used in industries, and it can be used in pharmaceutical industries. So again this is going to help dendrimers, which are also a type of nanomaterials. And last, it is used in bioimaging. So this is next application, bioimaging and biomolecular imaging. So these are the applications of nanomaterials. So if I summarize the whole nanomaterial part 1 and part 2, then nanomaterials, they are the components, they are any structured component, if it is having even if one dimension in nano range, then it is considered as a nanomaterial. Then why nanomaterials are important? Because if I take a bulk material, suppose I take this chalk, then the properties of this chalk will be determined by taking average of all the quantum forces which are operating on this. Now if I start cutting this and keep on cutting it, it will become smaller and smaller. A point is going to reach where the averaging of the force operating on this is not possible, or it does not hold good. That state we say that now we have entered into the nano range, because the properties, as we were determining the properties, they could not be determined now. There we say now that now we have entered into the nano range, and once the particle enters, or atom or a molecule or a macromolecule or any bulk material enters into the nano range, the properties they change drastically. For example, platinum is an inert metal, but it functions as a catalyst. Gold is solid at room temperature, but once we enter the nano range, it becomes in liquid state. So these are the importance of nanomaterials, why they are important. Next, we have got three types of nanomaterials: quantum well, quantum wire, quantum dot, depending upon how many dimensions are present in the nano range. In case of quantum dots, all the three dimensions, they are present in nano range. Then quantum dots can be prepared by two ways: either bottom to top approach or top to bottom approach. And then we have got different methods for the synthesis of nanomaterials, which is ball mill, sputtering, laser beam, radio frequency plasma method, and Solon gel method. Then we have taken up two examples of carbon based examples of nanomaterial. One is fullerene, the other is carbon nanotubes. Fullerene, it is an Archimedean solid. It is a polymorphic allotrope of carbon, where the discrete molecule contain a cluster of carbons, where C60 fullerene is the most useful, and which is known as Buckminster. The structure of fullerene is like a buckyball, where we have got hexagons and pentagons. We have got 32 faces. Out of 32 faces, 20 are hexagons and 12 are pentagons. And if you see the arrangement of fullerene, then we cannot have two pentagons adjacent to each other. We can draw two hexagons, but we cannot draw two pentagons adjacent to each other. So this is the structure of fullerene. Then if we come to preparation, we take two graphite rods, we produce an electric spark in inert atmosphere. When we produce electric spark, the graphite, it evaporates in the form of dust. Then that dust is mixed up with solvent, and after mixing up with solvent, we get mixture of fullerene, and then mixture of fullerene can be separated by sublimation or by chromatography. And next we have got properties. The color of the fullerene can be brown to black. So it is going to vary when we are going to vary the size. It is an insulator, but if I add an alkali metal, it can function as superconductor. It can function as a ferromagnetic substance if I add an electron donor impurity. Then the size of the fullerene can be reduced to 30%. without disturbing the cage like structure. Then we have got the applications of fullerene, like it is used as ferromagnetic substance, it is used as a superconductor, it is used in catalysis, and it is used in polymerization. The next example is carbon nanotubes. So buckyball, if we go on increasing the size of the buckyball, or buckyball of a very large size appears in the form of slander. So that is known as carbon slander, but later on it was known as carbon nanotubes. If we draw the structure of carbon nanotubes, then hexagons are present in the middle, and where the tube is going to close, or top or bottom, there we have got pentagons. So in case of carbon nanotubes, 2 pentagons can be drawn adjacent, but in case of fullerene we cannot draw 2 pentagons adjacent to each other. Now carbon nanotubes, they are of 2 types: single walled or multiple walled, depending upon the number of graphite sheets which are being rolled. If it is one graphite, then it is single walled. If it is more than one, then it is multi walled. Then on the basis of direction of rolling, whether it is rolled vertically, or it is rolled horizontally, or it is rolled diagonally, we have 3 types of carbon nanotubes: zigzag, armchair, and chiral. And after that we have got applications of carbon nanotubes, we can say, or nanomaterials. So we have got different applications of nanomaterials. So this is all in nanomaterials. Thank you.